out section 4.3. It's a little less theory, a little more algebraic, a little more straightforward. So if all those corollaries and theorems were not making you happy, this will be a little bit of a comfort and relief for you. So this is monotonic, sounds like a disease, functions, and the first derivative test. Monotonic functions and the first derivative test. Sounds impressive. Okay, so a little bit of a warm-up or a preview, I'll call it a warm-up to this, is what we're really talking about in this section, they're pushing really hard in this section, is they're wanting to talk about intervals in which the function is increasing and decreasing. Intervals in which the function is increasing and decreasing. So let me draw a function to the best of my abilities to try to emphasize this. Something like that. Okay, so f prime of x equals 0 when x equals what? 2. X equals 3.5. And I was trying to make it happen, let's say at 5.5. Now, f prime of x is positive somewhere. And the way this question is going to be asked is, where is f prime of x greater than 0? Which is the same thing as saying, where is your first derivative positive? Where your first derivative is greater than 0 is, where is the derivative positive? In other words, this is asking, where is the slope of the tangent line a positive value? Okay? So the slope of the tangent line is positive, 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 positive until it gets over to 0. So between 1 and 2, the interval between 1 and 2, that's an interval. Where else? 3.5 all the way up to 5.5. Because at 5.5 is 0 again. And then 5.5 is 6, right? These are intervals. Those are U's, making unions of those intervals. That's where f prime of x is positive. That's where the slope of your tangent line is a positive number. Where is f prime of x negative? That's right, between 2 and 3.5. And that's it, right? Now, here's where the conclusion comes in. If the slope of the tangent line or the first derivative is a positive value, is this function increasing or decreasing? It's increasing. So the function is going up, it's increasing in this region. and it's always increasing in this region other than when it kind of levels out here. Okay, so when your first derivative is positive, your function f of x is increasing. Okay, when your first derivative is positive, when all the slopes of your tangent lines are positive, then the original graph, the original f of x, is an increasing function. What about when it's negative? Is f of x, the original graph, is then decreasing. Okay, so the original graph is increasing when your first derivative is positive and decreasing when your first derivative is negative. Now, and there's a big corollary that says this on page 199. And now that we've determined how it works, this will make sense without even having to write it down. It says, given that f is continuous and differentiable, when the first derivative is greater than 0, when all the slopes of the tangent lines are positive, then f, the original function is increasing. When the first derivative is negative, when all the slopes of the tangent lines are negative, then the original function is a decreasing function. And that's logical. You want to make that logical. Don't memorize that. You want that to be logical. It makes sense. So kind of keep a vision in your mind. Now, where it gets very interesting in here is they talk about whether your intervals of increasing and decreasing are closed intervals or open intervals. And it really seems that they kind of contradict themselves, because they say, where do they say this? Well, they talk about it, and they do contradict. And I don't have it marked because this is not the book I have at home where I underlined it. But they're going to want you to write these intervals of increasing and decreasing as open intervals with parentheses, not closed brackets. But I can't find it. But they're going to want you to have open intervals. Okay, so then they come up with questions like this. So we're going to go into an example now. And I'm going to have to go to another piece of paper. Okay, it says find the critical values of f of x and identify the intervals of increasing and decrease. Now, why do you think we need to find critical values? There you go. Your local maxes and local mins are your critical values. So you change from increasing to decreasing at your extreme values or your critical values. So your critical values kind of separate where you increase and where you decrease. So your critical values are giving those regions where you're going to change, your function is going to change from increasing to decreasing. Okay, so this is your function. This is a cubic function, a third degree polynomial. X cubed minus 12x minus 5. It is continuous, it is differentiable, there's nothing wrong with this cubic function. So we're going to come in here and we're going to find the first derivative, and then we're going to determine where the first derivative is negative and where it's positive, so that we can say where the original function is increasing or decreasing. So we're going to come in here and compute the first derivative, and the first derivative is 3x squared minus 12. And now we want to know, where is this negative, and where is this positive? Well, to determine where it's negative and positive, you make a sign graph. So we're going to have to create a sign graph. But to create a sign graph, we have to have critical values. So let's come in here and find our critical values. So our critical values are where 3x squared minus 12 equals 0, or where 3x squared minus 12 is undefined. Well, 3x squared minus 12 is not undefined. Okay, so in other words, you're looking for where f prime of x equals 0, or where f prime of x is undefined. Those are your critical values. So where f prime of x, that looks funny, I don't know what I did. Where f prime of x equals 0, this is where you have 3 times x squared minus 4 equaling 0, or 3 times x plus 2 times x minus 2 equaling 0. So your critical values are negative 2 and positive 2. So right now we're thinking these are probably where a local max and a local min exist. This is where the first derivative equals 0. This is where I have a horizontal tangent line. These 2 points are probably where I either have extrema, so that my first derivative should change signs. So now I create a sign graph, or a sign chart. You put your critical values in your sign chart. Your critical values are negative 2 and 2. And we normally put, we always do this in our sign charts. Okay, those are our critical values where this thing is probably going to have a local max and local min. Now, we want to know the sign of the first derivative, because if it's negative, the original function is decreasing. If it's positive, the original function is increasing. So this is my first derivative, right? My first derivative is 3 times x plus 2 times x minus 2. The first derivative is 3 times x plus 2 times x minus 2. So I'm looking at the product of x plus 2 times x minus 2. I'm looking for that product. Now, to the left of negative 2, I pick a test point. Maybe I do negative 10, a value to the left of negative 2. And I put it into the binomial and find out if it's positive or negative. If I use a negative 10 plus 2 is negative 8, which is a negative value. If my test point is negative 10, a negative 10 minus 2 is a negative 12, which is a negative value. If my first derivative is the product of these two, is my first derivative negative or positive? It's positive, because it's going to be a negative times a negative equals a positive. A negative times a negative equals a positive. A negative times a negative equals a positive, or a negative times a negative is a positive. Okay? Now, between negative 2 and 2, I pick a test point of 0. 0 plus 2 is positive 2, which is a positive sign. 0 minus 2 is negative 2, which is a negative sign. So their product is a positive times a negative, which is a negative. Over here to the right of 2, maybe I pick 10. I don't know, pick 1,000, whatever you want. If I pick 10, 10 plus 2 is a positive 12. So it is positive in this region. 10 minus 2 is a positive 8. So it is positive in this region. So the first derivative, which is a product of these two, is it positive or negative? It is positive, because it's positive times positive is positive. So my first derivative is positive to the left of negative 2, negative between negative 2 and 2, and positive to the right of 2. So that means this is my first derivative. That means that my original function, my cubic function, is increasing where the first derivative is positive, is decreasing where the first derivative is negative, and increasing where the first derivative is positive. So I conclude f of x, which is the cubic function, it is increasing from negative infinity to negative 2, and where else? And 2 to infinity. And it is decreasing where? From negative 2 to 2, where it is negative. We've answered the question. Now, it would be wise to check this, right? That might be a good idea to check this. How would you check it? How about I graph it? Let's graph this sucker. Let's graph this cubic function and see if this really works. So I'm going to graph f of x equaling x cubed minus 12x minus 5. Use that nice little calculator. Y equals, clear that off, it's a cubic function, x cubed minus 12 minus 12x minus 5. Well, I got this screen all unhappy. And I'm going to do a zoom, standard, relatively small screen. That might not be a big enough screen. Let me get my vertical values a little bit higher and a little bit lower. Let's let this be a negative 20 and a positive 20. There it is. That's a little bit better. A little bit better. So now, what's the x value at this local max right here? Negative 2. That's pretty logical, right? Isn't that what we figured? That was that critical value? What's the value of this min? Where's the x value at this value of this min? Positive 2. Is this function increasing from negative infinity to 2 and increasing from 2 to infinity? Is it decreasing between negative 2 and 2? Yes, it is. Okay. So going back to the camera, if I can find it. Here it is. Okay. So I'm even going to try to line this up with my sign chart. If this is my negative 2, and this is my, I didn't do that very well. This is my negative 2, and this is my positive 2, right here and here. Then this is not good. Then this went up, came back down, and went back up. So it was increasing, then it was decreasing, and then it was increasing. Okay, so even your sign chart, your function's increasing, then decreasing, then increasing, so that it had a local max and a local min. Now, would it be logical if your function is increasing and then it decreases, that this would be a local max? If you go from increasing to decreasing, wouldn't that create a local max? And if you go from decreasing to increasing, wouldn't that create a local min? Can you visualize from the sign chart kind of what's going on here? Y'all are zoning! You're like glazed over. You're just kind of bobbing your head up and down. You better respond or she's not going to shut up. Somebody bob well. Act like you know what she's talking about. You're just getting tired. Okay, you're just getting tired. So I'm going to have an FYI here. What time is it? I'm wearing you guys out because we're running out of time. Okay, real quick, because of what I just said while you're all zoning, okay, you're like brain dead. You're going, somebody answer her so we can just leave, okay? Somebody be really smart, okay? Okay, here's what's in the box. It says, if f prime changes from negative to positive, means it's changing from decreasing to increasing, it's going down and then up, then it has a local min. If f prime is changing to positive to negative, if it was increasing and then decreasing, it has a local max. And if the f prime does not change, it means it just stays decreasing or stays increasing, then we don't have any local max or local min, we have no extrema. So that's where it leads to. And we only got to do, what, one example? So we definitely have to continue this, but I think honestly you could start doing the homework in this section and be okay. But we will finish this on Wednesday when you are more lively. The look across the room's like, okay, somebody, it's either this or this, but somebody do something the right way. Yeah. We'll just believe you.